All right, thanks, Alex, for the introduction, and it's really a great pleasure to be here. And well, I can see that in Xi'an University you have a much nicer campus nowadays, and with this new building and very dedicated for research. And I'm really glad that this happened, and hopefully you guys will be doing even better in the future. So I realize that today we have a very broad audience. So today we have a very broad audience, people from various different backgrounds, and sometimes I might just keep talking about things that I myself feel very excited, but people might not even know what I'm talking about. So if that really happens today, feel free to stop me and ask me questions. Okay. I sometimes would rather have a more interactive audience. But what I'm going to talk about today is mainly about my own research work on decision making and neuroscience. So basically, well, nowadays with my talks, I normally start with this picture, and it really tells people how diverse my interest in, but in other words, how bad I'm at to focus on one particular field of work. I guess that summarizes what I'm interested in the way that, well, first of all, is interested in how people make choices. But not only that how people make choices are important to me, how our brain is important or take different roles in allowing us to make these choices in terms of the neurons or in terms of the whole brain as a total. But I also am interested in how we would be able to simulate what the brain is doing. Nowadays, you heard quite often about machine learning or artificial intelligence. Well, strangely, nowadays, decision neuroscientists talk a lot to those people. For the reason why is because now, if you are designing a machine to act intelligently, you probably need to teach the machine to learn something, and also you need to teach the machine to do some decisions. For example, well, a year ago or half a year ago, you heard about news about AlphaGo, and actually is a very nice example about how decision making or decision neuroscience has contributed to machine learning or artificial intelligence, because quite a lot of those work is built by our understanding of how our human brain works. But not only that, well, we want to do all these sorts of things with humans, we also are interested in doing the same thing with other non-human primates, for example, monkeys. There's a very good reason why we want to do that, because, well, we all would think that humans and those non-human primates, such as monkeys, we share the same ancestor. We share the same evolutionary origin. So if we know something about these other species, it might tell us something about how the human brain would evolve or some of the functions of the human brain. And in fact, sometimes with monkeys or animals, you can try and apply other research methods in order to do experiments with them. Well, of course, sometimes it's controversial, but we have to admit that this is one advantage of doing research using this kind of direction. All right, so why decision neuroscience? As I said, sometimes I get too excited about the work that I'm doing, and it's somehow quite boring to other people. But, well, decision neuroscience is done with the following hope. We hope that it could have some applications in the future. And I'll just briefly talk about several examples, but I won't go into too much details today because, well, to be honest, I myself haven't really worked a lot on these areas. But first of all, the most obvious example would be of clinical use, that if we know how the brain works, we can make predictions if we have a patient, for example, that suffers from head injury, certain parts of the brain is broken. We can try and predict what will happen with that particular person and try and devise ways to help these people. Well, of course, nowadays Hong Kong is quite mad with the property price, and it's really a major lifetime decision if you go and buy a flat. Probably you wouldn't want to make poor choices if you are buying a flat or making a very important decision like this. So if we know more about how the brain works, perhaps we can find out ways in order to help people, in order to make choices that they really like more. Well, obviously, sometimes we make choices that we regret. If there are ways that we can reduce the possibility of people making choices that they don't like themselves, that would be really helpful. Well, other example like Brexit, well, I guess one of the very clear example of how people sometimes might not be able to really make wise decision. I'm not sure whether this is wise or not. No opinion on that. And finally, I've mentioned AlphaGo, that if we know more about how people work, probably we can develop better artificial intelligence that would probably help us to improve our life quality. All right, again, as I said earlier on, I'm quite strange that I'm more interested in boring stuff. And this is the most boring example ever, but I talk about it quite a lot. Which is something quite trivial. Every day we make decisions. If you go for lunch, later on you are making decision whether you want to go to this restaurant or that restaurant, or you want to choose this dish or that dish. For example, if you have the following choices for your dinner, you might be choosing between 3 options: a lobster, a nice steak, and a sandwich, so to speak. So let's say, well, money is not an issue, somebody's treating you, then probably that sandwich doesn't look very appealing, probably. So you might think that, well, lobster or steak might be better, and you would then choose one of them, okay? So this actually tells us a lot about the decision-making process. Although, well, just now, this example seems like a very, very trivial process. But in fact, quite a lot of things happening in our mind. When we are looking at these pictures, or even just the words, like on the menu, you see the word lobster, steak, sandwich. When you're reading these words, or when you're seeing these pictures, what you have in your mind is perhaps the taste of the food associated with those words. You might be, well, thinking how the lobster would taste, and whether it tastes good or tastes bad, whether you yourself like seafood or not. So there are quite a lot of things happening. And you would do the same for the steak and the sandwich as well. And then in order to enable you to make a decision, what you have to do is to compare between the goodness or the value of the options that are presented to you. So now, well, if I try and summarize what has just happened, you are trying to undergo this process of valuation, or knowing the value of each individual option. You also try to compare the value between the options. In other words, it seems as if these different options are competing against each other. So the options with the highest value would win this competition. And lastly, well, sometimes the lobster, well, let's say if you have chosen the lobster and you have consumed it, it might taste better or worse than you thought, okay? If that happens, probably you would need to reevaluate how good a lobster is. Or let's take the most extreme example. If you get food poisoning with lobster, then next time probably you wouldn't take the lobster anymore. But why that happens? Because of the updating process. You update the value of the lobster. So well, people has been interested in these different processes. I'm not saying that the three processes are the only processes that are involved in decision making, but this helps us a lot how to understand how we make decisions. And early works in decision neuroscience thinks that the orbital frontal cortex of the brain is one key region that is involved in decision making. So for those who are not familiar with the brain, so this is the human brain, this is the monkey brain. Okay, imagine that we are looking at the brain from the bottom view. So probably we'll have the eyeballs from here that goes, which is on the top of the screen. Our eyeballs are there, and which is roughly here, and this part of the brain is the orbital frontal cortex, which is right above the eyeballs. So this is the part of the brain that I'm talking about, and this is the equivalent for the monkey brain. So early works by Damasio and colleagues, they try and test patients with a lesion in this particular brain region. And this is one of the examples of the patient. You can see that, well, there's quite a huge damage in the orbital frontal cortex. Again, these are the eyes, and this part of the brain, which is about the eyes, is the orbital frontal cortex. And what they realized with these patients is that, well, they seem rather normal, but they have some subtle, strange behavior. And they realized that if they try and test these patients with a task called Iowa gambling task, they behave quite strangely in this task. So what those patients did in that task was that there are different decks. Okay, there are different decks of cards there. They have to choose between these different decks in order to win money. Okay, it's like gambling, but some decks are better than the other. And they realized that these patients fail to choose the good decks as often as the normal people. Okay, so basically, this is quite a rough idea about, well, how damage in the orbital frontal cortex would be associated with poor decision making, as shown in this gambling task. So, but here, well, now we are in the 21st century. There are a lot of advancement in neuroscience. We can measure the brain in a more precise manner. So this is actually quite a huge damage. But now people are looking for more precision rather than just this huge damage. So if we look at the anatomy of orbital frontal cortex, well, we can loosely split the orbital frontal cortex into three subregions. Okay, I give these three subregions the following labels, but sometimes if you read papers written by others, they might refer to the same region by using different labels. Okay, but make sure that we are on the same page. I'll use these labels. Okay, so if I try and take this part of the brain, the orbital frontal cortex, out, or, well, this is the right-hand side, this is the left-hand side. If I take the right-hand part of the brain, it looks like this. And I can loosely split it into three parts: the blue region, the yellow region, and the green region. The blue region, because it's in the middle of the orbital frontal cortex, or the medial side, I call it the medial OFC, medial orbital frontal cortex, or the ventral medial prefrontal cortex. Well, I will use these two terms interchangeably in this course, in this talk. The reason why is because there are no clear boundaries between these two labels. Basically, people use these two labels interchangeably. The second region is called the central orbital frontal cortex, the yellow region. Well, obviously it's at the center. And the third region is the lateral orbital frontal cortex, this green region here, which is on the most lateral side of the orbital frontal cortex. What I want to do today is to walk you through my work, well, not just my work and some other people's work, that try and look at how these three regions would contribute to the decision-making process. And I'll use the framework of these three processes that we simply split the decision-making process into valuation, learning, and competition. So one piece of early work that helps us to understand how the orbital frontal cortex is related to valuation is an experiment like this. If I tell you that these dots are related to a piece of fruit, blue dots are related to apples, and orange dots are related to orange, obviously. So if I give you an offer like this, whether you would like to choose 4 apples or 1 orange, which one would you like? Apple, orange? Okay. Apple, okay, great. So basically, what you had to do is, again, like what I said early on, you need to imagine, well, these dots are related to apple, first of all. And you also need to think, well, how much do I like apple? And the amount of apple that this person is offering me. And you would do the same with the orange. Okay, so this kind of process, you need to evaluate how good this option is compared to the other option. And so basically, early studies have tried and look at this process and see how the central orbital frontal cortex in yellow here would have an important role in this process. The reason why people are interested in looking at the orbital frontal cortex in this kind of process is because of its anatomical characteristics. So the orbital frontal cortex actually is connected to many other sensory regions. So these sensory regions involve visual regions, auditory regions, and gustatory, olfactory, and so on and so forth. You can see that, well, when we are doing this kind of task, we need to associate this visual feature of the 4 blue dots with the underlying taste of 4 apples in order to allow us to make this kind of decision. So the orbital frontal cortex, because of a connectivity profile, makes it a very, very ideal place for this kind of process. Well, because it receives information from the visual cortex or auditory cortex and olfactory cortex. So if we have a region like this, it seems that it would be having a role in integrating the visual and olfactory information, or gustatory information, like the taste of the food. So that's why it's a very good region. And that's why in 2006, Padilla Chopra, they try and run the following experiment. Well, instead of offering monkeys an apple or an orange, well, I guess they might have some financial problem in the lab because they are just offering juice, which is probably much cheaper. This would mean 4 drops of juice rather than four apples. This would mean 1 drop of orange juice rather than 1 orange. Okay. So, but the monkeys were rather thirsty at that time, and they are very keen on working on this kind of task. So what they did was that they have monkeys performing in this kind of task, and at the same time they were recording the activity of the central OFC neurons. And what they found was that when the monkey was offered the options, the central OFC neurons become very active. Okay, these neurons are very, very excited. Okay, and also if the monkey really have the chance to taste the juice, these same neurons are also very excited. But there's one more important feature with these neurons. So if they try and look particularly at the activity at this time, when the monkey was offered the juice, the options rather than tasting the juice, they realized that this activity, the height of the activity, would correlate with how much juice the monkey was offered. So if the monkey was offered a very nice option, let's say 4 drops of juice, these neurons will become very, very active. But if the same option contains less amount of juice, let's say just one drop of juice, the same neuron will become less active at this particular period of time. So now you can see that, well, the activity of the neuron is correlated with the value of the option. And that makes it very useful in order to allow the monkey to know how good the apple juice offer is and how good the orange juice offer is. So that would be one piece of early work that helps us to understand how central OFC is important to evaluation. All right, this part is short because, well, I don't work a lot on this part, but I work a lot more on the other two parts. Okay, so next I would like to tell you about some functions of the OFC related to updating the value or learning. Okay, so if we want to know how people or animals update values, very often in the laboratory we can offer an experimental subject the following task. Each time, the subject will be given two options at a time. For example, this blue picture and this yellow picture. People wouldn't know which picture is a better picture. A better picture means that it is a picture that is associated with reward. Reward can be money, or can be food, or can be juice. If people are offered this kind of task, they need to find out which one is the good option by trial and error. So, for example, if the person has chosen this blue option and that option leads to a reward, then very likely the person or the animal needs to choose this same option again and again in order to gain more reward. But if the person or the monkey have chosen the yellow option and that leads to no reward at all, they realize that this is not a good option. Then because of trial and error, they would probably choose the alternative option. Okay. So if we try and plot it like this, we have a period of time when the blue option is rewarded and the yellow option is not rewarded. But one key feature about this task, in order to call it reversal learning, is that the contingency between the blue and yellow option would reverse in the middle of a task without telling the person or the animal. So all of a sudden, the previously good option would now become, well, the good option would now become the bad option, and it would lead to no reward at all. If that happens, and also the previously bad option would now become a good option. Okay, so this kind of task actually mimics the real-life changing environment. Like, for example, the lobster was previously very good to you, but on one day you suddenly get food poisoning, and the lobster now becomes very bad, and you should change your understanding about the lobster. So this task is very useful for helping us to understand reversal learning, or how people update value because of the change and the requirement of changing behavior. So basically, this task has been used for nearly half a century, but still it still has been using to test different research questions. One early work was conducted by Chau in the 60s. What he did was to train monkeys performing the task that I just mentioned, and then they try and look at how much errors the monkey has committed. For example, I just realized that they didn't have a normal monkey in this plot. But let's say this is a normal monkey. This monkey shows that, well, he or she has committed little error during the task. The monkey was good at changing their behavior when they detected there's something wrong with the environment and the environment has changed. So the y-axis here shows you how much error the monkey has committed. So they realized that if they try and impose lesion to the monkey's brain, there are many parts of the brain, even when it's damaged, the monkeys are doing perfectly fine with this kind of task. But there's one region that is very important to this task. If this region is damaged, then monkeys would commit a lot of errors in this kind of reversal learning task. And that particular region is the orbital frontal cortex, which is this whole region here and this whole region here. So because of these kinds of results from early works, people have long thought that, well, the orbital frontal cortex is important for reversal learning. But just a few years ago, there has been a new study trying to challenge this view, whether or not the orbital frontal cortex is important to reversal learning. What they did was that, well, going back in the early days in Chau's butter, well, they didn't have very good technology. Microscope was not very good, and they try and impose a lesion in the monkey's brain, maybe using their bare eyes and using some suction, and that would cause a physical damage. But recently there has been new development in order to improve this technique. So nowadays, what people can do when they are doing a lesion, they can try and inject some toxins into the brain. And these toxins are well made such that only the gray matter of the brain is damaged. The underlying white matter will be preserved. Okay, so for those who are not familiar with gray matter and white matter, so basically, white matter is a part of the brain that connects different brain regions. And when we are calling when we're labeling a region the orbital frontal cortex, we are talking about the gray matter, which is this highlighted region. And this white region is the white matter, and it is not the orbital frontal cortex. In the early days, when Charles Butter was doing the experiment and other people was doing these kind of experiments, they would physically damage the orbital frontal cortex. And what would happen, very likely, is that many of those monkeys might also have the neighboring white matter also damaged. So that means that when they're doing that experiment, they cannot just damage the orbital frontal cortex. So Peter Rudeberg, a few years ago, they want to compare the old method and the new method of using drug in order to damage the orbital frontal cortex and see whether both monkeys, monkeys damaged by one method or the other, have reversal learning impaired. What they realized was that if they use the old method like in the old days that Charles Butter has performed, the monkeys perform badly in reversal learning. But strangely, if they use an improved method by just damaging the gray matter, they could not see the same pattern at all. These monkeys are totally fine when they're performing in the reversal learning task. So what it means is that, well, it seems that the early results has been confounded. It seems that the orbital frontal cortex, if is cleanly damaged, but the neighboring white matter is preserved, is intact, then reversal learning is not impaired, and that would mean that maybe the orbital frontal cortex is not related to reversal learning. I'll skip this part, but I would also want to emphasize one part. The region of lesion conducted by Peter Rudeberg was actually lying at the central OFC and the medial OFC. But they did not damage the lateral OFC. Okay. So that's why after Peter Rudeberg's study, where in the brain is important to reversal learning is still an open question. So that's why back in those days, I tried to run the following experiment. I tried to train monkeys to perform in the same task. And I also had these monkeys performing in the MRI scanner. Okay, so they were sitting nicely in the MRI scanner, performing in this task and enjoying the juice, but inside the scanner. And the advantage of doing that is that I would be able to look at the whole brain, where in the brain is important to reversal learning. So basically, this shows you the behavior of the monkeys. So trial 0 shows you the time when the monkeys just had a reversal. So they need to update and learn the new environment. You can see that early in the reversal, the monkeys were quite bad at finding the good option. But the monkey would improve gradually by trial and error. So they would keep choosing one option and realize that, well, that option no longer would lead to juice reward. Then the monkey realized that they should shift to the other option, and they would improve gradually and perform very well later in a block. So basically, what I needed to do when I was analyzing data was to look at what would be a good strategy when the monkeys are doing this kind of task. So one good strategy would be the following. I call it a win-stay-lose-shift strategy. So if the monkey choose an option and that lead to a reward, we call it a win-stay trial, because the monkey should pick the same option again. Okay, if they choose an option, there's a reward, then the monkey should choose the same option again. As opposed to the alternative strategy, if the monkey has chosen an option that leads to a reward, but the monkey shift to the other option, that would be a suboptimal strategy. That's something bad. The monkey shouldn't do it because that will lead to no reward. The same would hold for the lose trials when there is no reward. When the monkey chose an option that leads to no reward, the monkey should shift to the alternative option, but they should not stay with the same option, because even if they keep choosing the same option, there will be no reward. So the monkey should shift to the opposite. So there are two good things that the monkey should do, win stay and lose shift. There are two other bad things that monkeys should not do. So as I said, I collected fMRI data with the monkeys. We recorded brain activity. And what I could do was to look at brain activity when the monkeys were doing the right thing of changing their understanding of their environment. They shift to the new option when they realize there is a change in the environment. And I realized that when this happened, when the monkeys were doing this task well, updating the value, this lateral OFC region is highly active. This shows you how the activity would change across time. When the monkeys were performing the trials or the task in a very optimal way, this region is highly active. Well, there are variations across the monkeys. Some learned quicker, some learned slower. And I also try and correlate their learning rate with the activity of the lateral OFC. What I found was that for those monkeys that learned more quickly, this particular region was also more active. And this shows you an evidence that the lateral OFC is very important for updating of the value in the changing environment during reversal learning. So now, you might find it strange. Just now I talked about Peter Rudebeck's study telling you that the orbital frontal cortex seems not important to reversal learning when they use the new technique. And now I found that the lateral OFC is important for reversal learning. But if we try and put these two pieces of information together, there's something quite interesting. Peter Ridderback actually did not impose a lesion at the particular part of the orbital frontal cortex, which is the lateral orbital frontal cortex. So if they were able to impose a lesion in this adjacent region, maybe it is possible for them to see impairment in reversal learning of these monkeys again. So this particular region also has some very interesting anatomical characteristics as well. So this is one early work by Carmichael and Price. They try and look at many different subregions in the orbital frontal cortex and try and look at their connectivity profile. They realize that, well, the orbital frontal cortex basically are connected as if there are two clusters. There are some orbital regions on this orbital surface that are more likely to be connected with each other. There are some other medial regions like this part of the brain, orbital region like this part of the brain. The medial regions are more likely to be connected to each other. But they realize that these two regions, the orbital network and the medial network, they don't talk a lot to each other. There are little connectivity with each other. But interestingly, if we look particularly at this part of the orbital frontal cortex, the lateral OFC, which they call area 12O, it has connectivity, strong connectivity across all the different orbital frontal cortex regions. So it seems that, well, this region is particularly important if we need to integrate information, especially in a changing environment, in order to update our understanding of value. So that's why I would think that, well, that would make it a very ideal region for this kind of purpose. So far I've talked about how I can see interesting findings. Well, personally it's interesting, not sure interesting to you or not, but findings about the lateral OFC and how it's related to reversal learning. But sometimes fMRI experiments are criticized by, well, first of all, we don't know whether the signal that we found was a decision signal or post-decision signal. Okay, whether it's a signal that really drives people's decision making and updating, or whether it's just a byproduct of this process. That means that if it's a post-decisional signal, then that would mean that this signal is not directly to the updating or the decision itself. And also, with fMRI study, we can't show any causal relationship. And there's a monkey study, and what about humans, and whether we have any clinical implications. We had all these questions in mind after this experiment. So that's why we then conducted another follow-up experiment. So I and my colleagues in McGill University performed this experiment with patients, human patients with stroke and brain tumor. Okay, so now we don't deliberately impose any lesion to humans, of course, but we try and be patient and slowly recruiting these stroke patients or patients with brain tumor in our experiments. And we try and do it very carefully as well. We try to be very selective. We included one group of patients with focal lateral OFC damage. So this shows you where in the brain these patients were damaged. So you can see that, well, this part of the brain is the lateral OFC, which is a similar region that I've just shown you in the monkey data. We also collected two control groups. One group of healthy controls and one group of VMPFC patients. So this is, as I said, we sometimes also call it the medial OFC. So there's another part of the OFC. So we basically try and ask these patients to perform a very similar task that we asked the monkeys to do. But of course, well, this task might be a little bit too simple for humans, so that's why we try and make it slightly more complicated. Basically, with this task, they were choosing between 3 options, but similar to the monkey task, one option was initially good and become bad, and might become good again and become bad. So these patients, when they're performing this task, again, they need to work out by trial and error which one is a good option. So what we found was that when we look at the decision accuracy, or whether they would be able to choose a good option in these patients, we realized that it was the only lateral OFC patients that were impaired in this task. So now we found some evidence showing that, well, it's not just the signal in fMRI data. When we try and see the behavior of patients with the damage at this particular brain region, we also can see an impairment in reversal learning. So this gives us some idea about the causal role of lateral OFC in reversal learning. So, okay, so because of time, maybe I need to skip these. All right, so, and well, just to share with you just a couple of weeks, well, this plot actually is giving you a very similar result to what I just mentioned, that the patients were not able to update very quickly, and they made more errors when they were performing in the reversal learning task. And just a couple of weeks ago, Peter Rudebeck, the authors that I just mentioned, they also conducted a very similar experiment with monkeys. Now they make a lesion at the orbital frontal cortex, central and medial, and with other groups of monkeys, they made a lesion at the lateral orbital frontal cortex, and they realized the same result in the monkeys. So basically, we found that lateral OFC is important for reversal learning in monkey fMRI, monkey lesion data by Peter Rudebeck and colleagues, and we also found it in humans as well. All right, because of time now, I should quickly go into the last part. Again, I might need to skip some of the details, but feel free to ask me later on. So far, we've seen that the central OFC is important for valuation, understanding the value, or knowing the value. The lateral part of the OFC is important for learning or updating the value. Now I would like to talk to you. I would like to talk about where in the brain is important for comparing value or competition between the options. So obviously, well, there's one part of the brain, one part of the 3 that I haven't mentioned, and it's really that region that's important for comparing values. So there are many different studies that have provided evidence showing us that, well, this particular part of the brain is important. For example, if we, again, are making this kind of trivial decisions, what we need to do is to understand the value of the lobster and the steak and try and compare between the two. And this comparison, or the value difference, which is a critical index showing us whether the brain is having a role in decision making or not. We found, well, people found that in the medial orbital frontal cortex, or the ventral medial prefrontal cortex, this part of the brain encodes the difference in value between these two options. And this is very important evidence showing that this part of the brain is important for decision making and comparing values. Since this kind of understanding of the VMPFC has long established, what I myself was more interested in is that, well, there has been a lot of experiments that try to look at what happened when there are 2 options, but there are much less experiments that look at what will happen when people are making decisions between 3 options or multiple alternatives. So that's why I try and design an experiment like in the restaurant that we're choosing between three options. But I would ask the following question. Well, if the sandwich is so bad, probably you would just simply ignore it. And if you are rational enough, probably you would just make a decision by considering between these two options. And you would just totally ignore the very bad sandwich. But let's say if I change the sandwich to something, well, let's say you hate salad even more, or not sure whether you would like this or not, or even you can see this. This is some sort of, this is food. This is deep fried scorpion, and I haven't tried it myself, but I guess you probably wouldn't try it. Probably this is the worst option that you can ever have, I can imagine. So, well, if I give you decisions in these three different ways, showing you lobster steak, changing your sandwich to salad, or changing your sandwich to scorpion, probably these very poor options should not have an impact on your decision making, right? But strangely, we humans don't behave like this. Even if these options are totally irrelevant, we will still take these options into consideration, and they are still having an impact on our decision making. But the next question is how? So in my experiment, I try and conduct a three-part investigation. I try to do some biophysical model by making simulation using computer and try and mimic how a decision network in the brain would work. And I also tested human behavior and try and record brain activity using fMRI. Because of time, I don't have much to say about the model, but what I can tell you is that there are different predictions made by different models, well, I'll probably skip the modeling part, okay, and go strictly to human behavior. So what I did in the lab was, of course, not asking people to choose between lobster and steak. Well, this is too costly for me. So I'll try and do something simpler and cheaper. What I did was to ask people to choose between three options. These abstract stimuli, each of them would be related to an option. So each of these stimuli is associated with two information. The color of this bar is related to how much money the person can get if they have chosen this option. But the angle of the tilting of this bar is also related to the chance of getting the amount of money. For example, this bar is the same as this one, which means the person, if they have chosen this bar, have the chance of getting £8. And the chance of 62.5%. Okay, so it's like a gambling task, right? People are choosing between different options that are associated with different size of monetary reward and different probability of getting the reward. But also, I try to make this trick. There are three options, but there's always one option that I made it a distractive option. By showing a purple box surrounding the option. So if that happens, the person or the participant shouldn't choose this particular option, and they should choose the other two alternatives only. And by doing that, I would be able to see systematically how the change of the value of the distractor will have an impact on people's decision making. When I said the change of value, it means that if I change it from a low reward option to a high reward option, or from a low chance option to a high chance option, whether this distractor would have an impact on people's choices. All right, so when I was looking at the data, I tried to look at two key parameters. So the first parameter is the difference in value between the better option, well, the better option, I call it the HV option, and the LV option, the worst option. how much the H3, the better option, is better than the poorer option. And I'll also look at how often the person would be able to choose a better option in terms of the accuracy. So the first parameter, the H3 minus LV parameter, just show you something very trivial. When the better option is way better than the worst option, people were better at getting the best option, the H3 option, or accurate option. And when the two options are getting closer and closer together, people are less and less accurate in choosing the best option. So this is something trivial, nothing interesting. But then I also look at the second key parameter. On the left-hand side, I have trials where the distractor value was very high, and on the right-hand side, the distractor value was very poor. And if people are all rational beings, we shouldn't be affected by the change in the distractor value. And that would be the prediction. If people are rational, this landscape should look flat. But in fact, it was not really the case when we are looking at the real behavioral data of our participants. What we could see was that when the distractor value becomes worse and worse from the left to the right, people actually make more inaccurate choices. People are less accurate in making decisions. So that means that, well, good distractor actually helps us to be more accurate. Poor distractor actually makes it less accurate. And then what we looked at was to, and then what we did was to look at the brain activity associated with these kinds of behavior. As I mentioned earlier on, in the medial orbital frontal cortex, there is a key signal that is related to decision making, and we call it value difference signal. And we try and look particularly at this signal and try and see what will happen when the distractor becomes poorer and poorer from the left to the right. So if we plot the strength of this value difference signal, we realize that on the left-hand side, when the distractor value was high, the VMPFC activity was also stronger. On the right-hand side, when the distractor was poor, the VMPFC activity was also weaker. So, and this pattern was also similar to the pattern that we found in the behavioral data. When people were more accurate, these are the trials when the distractor was good and the VMPFC signal was stronger. And when people's accuracy was poor, it was also related to poor activity in the VMPFC. So recently, I'll spend 5 more minutes on this very last part. And recently we asked a question, well, if we manage to show people some options, and we saw people press a button and make a decision, what will happen in between? So that's why recently our lab was conducting the following experiment, and we had to have help of Kelvin Law and Michael Wu, which are sitting over there, smiling now. And what we did was to run an eye tracking experiment. We try and look at how people would evaluate the options by looking at different options moment by moment. Okay, so it's basically a camera looking at the eye movement. And when we were conducting this experiment, there are some key features that we want to look at. We count the number of fixation at each option and see how it would correlate with the value of each option. And first of all, we found a very trivial effect. When the distractor value gets higher and higher, we also saw more and more fixation with the distractor. So basically, there's a positive correlation between the value of the distractor and how often you look at the distractor. But then we also look at the next thing, which is more important, which is, well, if the distractor value is high, whether we would then look at it and shift to other options. And what we found was the following. We found a positive correlation between the distractor value and the shift between the H3 and D option, and a negative correlation between distractor option and the shift between LV and D option. So in order to understand this pattern, I'll just show you this figure once more. What it means is that, well, when the distractor is good, then you will have more shift looking between the better option and the distractor, and you have less shifts in your eye movement between the poorer option and the distractor. And when the distractor becomes even poorer, you would end up with something quite strange. You will shift more between the bad option and the distractor, and you shift less between the good option and the distractor. So finally, I also want to look at whether this shift is directional, because, well, this is a double arrow, but maybe poorer distractor might promote you to look at the distractor, then to the LV option, or the other way around. So what I did was the following. I try and look at the directionality of this pattern, and what I found was that there was a positive correlation between the shift from distractor to H3, which means that if the distractor becomes poorer and poorer, you would look at the distractor, you would look away from the distract to the LV option, and that would help us to understand why we found that behavioral pattern. So overall, what I told you was that, well, when the distractor value was poor, you would have more distractor to LV gaze shifts. You would also have a poorer, weaker signal in the VMPFC, and finally, you also end up with poorer decisions. So this is basically the summary of my talk. Today I told you, I introduced 3 brain regions in the orbital frontal cortex, the central OFC, the yellow part here, which is important for evaluation. The lateral part, LOFC, is important for updating and learning, and the medial part is important for our decision making to compare between options. And I also told you some findings about how the third option would have an impact on people's decision making by changing people's decision, changing people's gaze shifts or eye movement, and changing people's brain activity. So this is the end of my talk. I would like to thank the following people. People in our lab, Kelvin Law, Michael Wu, Tinkin Hong, who has been very helpful in all the technical issues. My collaborators in Oxford, my collaborators in McGill and the Japan CNET, and my funding bodies. And there's one last thing. Alex just mentioned before my talk that if you want to receive more information about cognitive neuroscience events in Hong Kong, we have a mailing list called Hong Kong. Cog means cognitive. Hong means Hong Kong at googlegroups.com. But simply, you can just send me an email if you want to be in part of that mailing list. It helps you to receive information about seminars like this or other kinds of events. Okay, so thank you so much.